Cool. So I'm going to go ahead and explain problem number 30 in book 6 of Euclid's Elements. He wrote this in like 300 BC, probably got it from Pythagoras. He doesn't really say who he got it from, but this is the first instance of the golden ratio Fibonacci sequence that I've come across in history. Probably got it from the Chaldeans, though. I don't know. Anyways, in this problem, you're given a straight line, which is this line right here. For now, don't worry about the dotted line section. It's just this whole thing is one line, treat it as one line. And on this line, you're going to go ahead and square it to make this blue, yellow and blue square, which is here. Because if you multiply this by this, you're going to get this square. You're squaring this. And on this square, you're going to go ahead and make a blue line, which is one of the sides. So that's this blue line that's right here. And this blue line is equal to the original line we had because it's a square, and that's just one of the sides. And now you're going to go ahead and add an extra piece to that original blue line such that the entirety of this blue line, which is here, multiplied by the extra piece that you just added, is going to be equal to the original line that we had squared, right? Which we know the original line we had squared is this. So ultimately what it's saying is that this line right here times this section is going to be equal to this, the area of this square right here, which is this original line squared, right? So now we're going to go ahead and segmentate the original line right here at this special spot right here, such that the larger segmentation is going to be equal to the extra portion we added to the original blue line earlier. So this section right here is going to be equal to this section right here. And if you do that, you can go ahead and make a square by making a black line parallel to the blue line, which is this one, and a yellow line parallel to the red line, which is this one, to get this white square right here. So the ultimate argument is that this rectangle here is going to be equal to this square here, and he goes on to explain that. Because if you have, so then you have this yellow and white rectangle is going to be equal to the entirety of the blue line times this section of the blue line. Because this section is actually equal to this yellow line, so you're just multiplying this line times this line to get this area, which makes sense. But if you remember, we said that we made this blue section such that the entirety of this times this section is going to be equal to this square. So since that's essentially what we have, he's saying that this rectangle is going to be equal to this square, because that's how we made this blue line specifically. So since we have these two equal parts, if we take away the common part, which is this yellow piece, essentially we're going to say that this white square is equal to this blue rectangle, because this is the same size as this, and we're taking away the equal parts. So what's left is going to be equal as well, right? So he's saying that this white square is equal to the square of the larger segment of the line from right here. So this red solid part squared is going to be this white square. And that the blue rectangle is equal to the original line multiplied by the smaller section right here, because this original line is actually going to be this side of the square multiplied by the smaller section, which gives you this blue rectangle. And so ultimately what it's saying is that this segment squared, which is this white thing, is equal to this, which is the blue rectangle. Now all of that is to say that now you have a line that was perfectly segmented into an extreme and mean ratio, because now the original line that you had, the ratio between the original line that you had and the larger segment right here is equal to the ratio between the larger segment and then the smaller segment. Okay, so the entirety of the line, the ratio between the entirety of the line and the larger segment is equal to the ratio of the larger segment to the smaller segment. And that's going to give you an extreme and mean ratio, and that actually is mathematically the Fibonacci sequence when you look at it algebraically. So that's very interesting. All right, cool. So now we're going to go ahead and explain some of the algebra behind why Euclid's extreme and mean ratio does represent phi, the golden ratio, the Fibonacci sequence ratio, which is 1.618, because the math behind it is pretty interesting. So if you remember, the argument was that the ratio of the entire line with the larger segment is going to be equal to the ratio of the larger segment with the smaller segment. So here we're going to represent the larger segment with A, so A be the larger segment, and the B be the smaller segment. So this means that the whole line is going to be A plus B. And then the ratio is, we're going to denote it with phi or phi, I'm not sure how to call it, probably just going to go phi. which is the Greek letter, but at the time I don't think he used that. We do use that now though. So the argument in mathematical expressions is that the ratio of the entire line with the larger segment is equal to the ratio of the larger segment with the smaller segment, which is equal to phi. Now, if you go ahead and simplify it, that means that we're given these two constants. We know that the ratio of the larger and the smaller is equal to phi, and the ratio of the entire thing with the larger is equal to phi. So these are our two constants that we're going to know for sure when doing this proof. So what you do first is you go ahead and divide the second term into two pieces, which you could do that mathematically, which is a over a plus b over a, which is the same thing as this. And then you go ahead and turn this into a 1 since a over a is just 1. And we know that b over a is just the reciprocal of a over b, which is equal to phi, which we know from the very beginning, a over b is equal to 5. So since this is just b over a is just the reciprocal of a over b, we know that b over a is just equal to 1 over phi, the reciprocal of phi. So since we know that, we can just substitute this reciprocal of phi with b over a to get this equation. 1 plus 1 over phi is equal to phi. And so from here, we can pretty much just set it up as a quadratic equation by multiplying both sides by phi, right here and right here. And you get phi plus 1 is equal to phi squared. You go ahead and rearrange these around a little bit, and you're going to get phi squared minus phi minus 1 equal to 0. And this is pretty much all you need for a quadratic formula, where a is equal to 1, b is equal to negative 1, c is equal to negative 1. And then here's the formula. You plug it in, you get these numbers over here, you get this equation over here. And if you simplify that, you get this 1.618, which is the golden ratio phi, figured out by Euclid and probably his predecessors, his teachers before that, all the way in 300 BC. So that's pretty interesting.